point is that you never get to z equals infinity. The geometry smoothly rounds off. This is actually not the ADS, but the compact direction here. And this is z equals 0, and they smoothly round off at some z equals z max. In terms of the metric, you have this ds squared is L squared over g squared, a of u, dx2. And again, in the ADS geometry, one has arbitrary low energy excitations by moving an excitation to smaller and smaller z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that, and so you have a mass gap. So whenever you find a relevant perturbation to a conformal theory, there's a good chance that all you're going to do is give mass to everything, and on the geometric side, that's reflected by capping off the geometry. Here, though, it works out that you've got this plus you have n minus 1 d3 branes, not n d3 branes, sorry. Carries exhibits exactly the massless sector that you would expect from the field theory. And the thing about Seiberg witness is the whole moduli space. These d3 branes actually have lots of places that they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. And actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking of this years ago, never forget. You know if anybody ever turned that out? Homer problem. Yeah, it's a great question. I mean, part of the problem is that the supergravity folks first have to tell us what the metric is for arbitrary distributions of d3 branes, because this trick gives you special distributions. If they would tell us what arbitrary distributions, then we could want to bring it to the argument and find out. Geometry picture of this is very important. You have to see some special to have this distributed for large ends. We don't really understand or just how it's for large ends. Okay, right. Right, you said we understand that for small number, where it might not be in the geometric regime. Good. Okay, with three masses, you try again the same trick. That is, you get some potential, you follow it off. The 5-dimensional solution you get lists to a singular 10-dimensional solution. A good question. This consistent truncation magic chooses a particular point in the moduli space. And of course, in fact, of course, when there's a moduli space, I mean, the consistent truncation is a solution generating trick that doesn't capture everything. For a while it was a goal to try to find the gravitational description of the general point on the moduli space. But it seems to be beyond the supergravity account. You don't have to be there, but actually describe the back reaction of the d3 branes. It seems like an open question. The people who've done the most on this are close to Warner, and they pushed on the problem, made some progress, but I don't think they ever gave a general solution. So, I think we're taking that any 5 solution can do it into a modification of heavy solution. No, it's not smooth when the fields run up to infinity. It's unique that it is a recipe. They look at the gravity of the equation, and it's a trick. And it's a trick which is one-to-one with now. In fact, let me come to it. When you get three masses, it becomes even starker because, let me see what happens with three masses. With three masses, you can do the same thing. The 5-dimensional thing blows off. You get a singular 10-dimensional solution, but it's not any recognizable sensible grade. No, this is in 2V, so there's no 11D left. Yeah, well, again, the two-mass singularity really is just d3 branes. Let me finish telling you what happens with three masses. So with three masses, if you're Max Strassler, you look at the gauge theory side of the duality for inspiration. If your superpotential is the W is m alpha, then the bone mass is equal, say, phi alpha squared plus epsilon alpha beta gamma commutator of phi alpha with phi beta phi gamma is all traced. And I'm leaving off the constants. Then the F-term equations tell you that, again, I'm leaving off the constants, m phi alpha is epsilon alpha beta gamma commutator of phi beta with phi gamma, which is to say that you have vacua for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2, then it just has to be reduced. So there's a huge number of vacua, including the trivial one, phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Kugel behavior. But remember that the scalar parts of these superfields arose as the coordinates of the d3 brane, and this is saying that those coordinates are becoming non-commutative. which comes back to the question from the last lecture, because Rob Myers explained that when you put D3 branes in a transverse flux, it becomes energetically favorable for the coordinates to become non-muting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with free masses is that it ends on, it actually ends on a D5 or an S5, or in fact, sums of many 5 branes. And the fact that there are many ways to calculate the geometry reflects the fact that the theory has many vacua. And so there's a nice match between, you learn from several things, but there's a nice match between field theory expectation and what Supergravity tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry that does, and in particular, it's useful to have insight from the gauge theory as well. By the way, you can, once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was steering this to the 5-dimensional object out into like a 6 or 7-dimensional object. And so it was trying very hard to get the right answer. Okay. Yeah, the last thing I want to say about this is I told you that one of these theories confines, and I want to tell you how to see that. So one observer I did talk about is to measure the potential between a source, a quark and anti-quark source fundamental, that maps so the QQ-bar potential. Fundamental. You can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it, in going back to Tufts and Wilson, is thought to be the color electric flux tube. And one could say more to justify this, but time is short. The way you calculate potential is to consider a string hanging down from the boundary, and then subject to suitable renormalizations, the potential is just the tension of that string. The potential is the total energy of that string, nothing from its tension. Now, the tension, the effective tension, so again, this is the Z direction, is the local tension times the gravitational relationship, the other way around, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further it hangs. And in fact, in an ADS phase, you get, as you must get, because just by its scale invariant as metric unit, as you pull the end further apart, the string hangs down lower, and so it can reduce energy and in such a way that the potential goes to the bottom. In a confining vacuum, on the other hand, we have to counter this idea that there's some Zmax. And so, the draw is a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the end further and further apart, and most of the string is just running along the bottom of the space at the largest value of Z, the most infrared value of Z you can get. And so the effective tau of the string is just non-zero. It confines. And that's what happens with free masses. With two masses, the Schrodinger's vacua are not confining, they're coulombic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the two masses, but it's also the D3 branes. And so now I'm going to draw the same picture. So here's Z equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those D3, so I'm looking now from a perspective that sees the 3 directions more explicitly, and so here's your D3 branes sitting at the bottom of the space, and the strings hang down. But once the string ends on a D3 brane, it doesn't go, it distorts its flux. But the flux is just a U1 gauge field, and it's free to spread within the D3 brane. So you get a Coulomb potential for a different reason than you did in the AES space, but it's still Coulomb. So that's the general thing with D3 proceed with. When a lower dimensional object dissolves in a higher dimensional, ends on a higher dimensional, it doesn't just end. There's always some set the arrows running the other way, I guess. There's always some flux carried by these objects, which has to somehow run through the higher dimensional object. But again, because the free range of the gauge field, the flux is spread freely. Okay, so that's the general idea of RG flows and also some specifics. Yes. I mean, you've got strings, you have G strings, and you have TQ bound sticks. So yeah, you have the entire sort of SL2 Z functional concept. So in fact, I mean, what these do is you also want to answer about the magnetic status of the magnetic field. And the magnetic objects are an analogous storage nodes. And similarly, you can ask for external ionic sources. Some CFTs have operators in the range between the minimum allowed by sort of unitarity, by the Coulomb algebra, and half the dimension of the space-time of the CFT. And this is the regime where, as we said, you have to take the alternate boundary condition, the less obvious one, on the scalar field at Z equals 0. But this is also special for another reason. It's special because 2 delta is less than Z. Less than Z. And so the double trace operator squaring the original operator is relevant. Now, and again, I'm using here large n factorization. In the large n limit, the amplitudes of the two operators at a point, and they're each connected to the rest of the graph, that the leading in n amplitudes are fully disconnected between the two operators, and so its dimension is just twice the original dimension. And so we want to see where this goes. And it's an interesting story. So, for a couple of reasons. Let's perturb. So we have our generating functional for the original CFT, and now we're going to add to it a double phase perturbation. And the nice way to think about this is to introduce an auxiliary field. And so understanding where this theory goes to isn't going to be so hard, because we can just use this trick to rewrite it in terms of the theory we know more about, the theory with just single phase operators turned on. And this is, in fact, specified the usual definition. Definition of sigma is minus 1 over 4g, and then the usual g plus sigma. That's just the generating functional for the single phase correlators. Okay. Now we can now do the sigma integral in a large n limit. We can now do the sigma integral just by saddle point. We can just find its saddle point. And actually, what this probably is the right answer beyond large n, but let's keep things simple. So let's evaluate this by saddle point, and the saddle point is at 1 over 2g sigma. The saddle point is at 1 over 2g sigma equals partial z partial sigma, which but this is just the generating functional. So differentiating at once with respect to the source just pulls down the expectation value. And if we go back to our original dictionary, a given operator in the CFT is just the normalizable mode of the quantized mode of the quantum field of the bulk. And so this is alpha, the quantized mode, as a function of theta equals j plus theta. The fixed mode is set to these values, and then you evaluate the quantized mode. And if we now plug in, rewrite what we have here is that 1 over 2g. Oh, actually, there's one of my C sub O's here. Some constant. 1 over 2g, beta minus j is equal to C sub O. So what you see is that introducing double phase perturbation is equivalent to introducing the boundary condition of this form. And there's some process all year. So if it's a And forget J for now, which is just again a source we're using to build a generating function. The basic statement is that we now have a generalization of the previous boundary conditions, where instead of 1 of alpha and theta being set to 0 or to a fixed value, they are proportional to each other with some constant proportionality. And we can now figure out, so now we can write it. Now, let me again, the J is not interesting, it's just again, the generating function. So to keep things simple, we now have, we can now write the mode expansion that phi is alpha z to the, plus beta z to the delta. We're in the regime where delta is less than d over 2, so this is the there's just some constant proportionality between them, so I can make one of these, I can write one of these in terms of the other side of the constant. This is one definite linear combination of these two terms turned on. And the point is now that if you go towards the boundary, this mode dominates. And it looks like the alternate quantization, the one that we started with in the UV to get that range of dimensions. But in the IR, this mode is the one that dominates, and it looks like the usual quantization in which delta, the effective density operator, is now changed to the minus delta. So what this is describing is a flow between the two possible boundary conditions for the given bulk mass squared. It's a flow. So what we call the alternate quantization, that is a quantization in which you have an operator whose dimension is in that range. That happens. It doesn't happen. There are no such operators in the n equals 4 theory, but in many variants of the n equals 4 theory, you do have operators whose dimensions are in that range. But in fact, as a sort of point of naturalness, that's unnatural, because if you turn on the double trace perturbation with even a small coefficient, the system will flow to the other solution with an operator moves up a larger dimension. And this has some relevance to the models of semi-liquids that Han will be talking about, where you have various flows going on in the theory. This example also exhibits another idea that's worth remembering, which is that if you look at say the second line there, the second line, we've taken the original AES CFT theory, and we've added a field sigma that couples to an operator from CFT. This is just an auxiliary field. Its action is just this local sigma squared. But you can imagine generalizing the structure and coupling fields in, whereas in a sigma squared you have some typical Klein-Gordon action or some kind of non-trivial dynamical action, or even some you could make thermodynamic operators have direct action. And what does this mean? What this means in this case is that your Lagrangian theory has two pieces. It has a strongly coupled piece, and it has another piece which may be weakly coupled or has just some implicit Lagrangian. And the strongly coupled piece has a gravity solution. These two pieces are coupled together through some interaction like that sigma O up there, some bilinear interaction. And so this is kind of semi-holographic, where you have the strongly coupled piece, and you're using gravity to solve the strongly coupled piece, and then you're coupling that solution to an explicit Lagrangian description of the other part of the theory. And again, this semi-holographic idea, it comes up in a lot of different places. There's no reason you can't, basically you're adding fields to the boundary theory by hand, and there's no reason you can't do that. It has a definite physical meaning, as I just said, and again, it comes up in these constructions that Han is going to talk about. Yes.
So look at the first line. The first is like if you're using a tree, if you're basically fitting yourself with a whole day comes from
right. So it's like in the n equals 4 theory, that's not invariant under the n equals 4 theory, so you wouldn't have it. That theory doesn't have this operator. But right. So in some cases, if you insist that your starting point preserves supersymmetry, then you don't worry about this. But from kind of a contentionality point of view, you have some UV theory, and you get the most, you get your most general Lagrangian consistent with the symmetries, which will usually contain such terms, which means that it's unlikely in this framework to find operators whose dimensions is in that field, the ultimate range. Well, that can happen in small. Okay, good. That can happen in small n. So indeed, and of course in the real world n is not so large, and so indeed we're talking here about things that happen within this large n universe that indeed may not need to be true at small n. Yeah. But at small n, the distinction between single trace and multi-trace begins to break down. When you get n equals 1, there's no distinction at all. When you get n equals 2, you've got single and double trace, but then couple trace are redundant. So the whole distinction of single trace and multi-trace is sharpest in the 1 over n expansion. Well, I actually assumed that sign to make it's attractive there, to make things work out nicely, which is the sign I also got from the references I was following. So we the notes, Seaver and Schomer and Berkmuth on this. The other sign is left as a homework problem. I'm not sure what happened. I mean, look, with the other sign, you can probably want to put an I in somewhere, and you get some complex saddle points, but I'm not sure if there's any significance to that. Yeah. Okay, actually, let's go on a second. I'm not sure what happened, actually. It's certainly, obviously, there's a big, so the sign really is saying that, the sign makes a big qualitative difference, because, and actually, it's an interesting question how it changes the topic.
There's something, I think, potentially suggested here, namely, if you had chosen the more complicated multi-level action for sigma, as an integral,
yes,
you would have gotten from complicated power series to O, including a lot of non-normalized center, which doesn't look like it makes sense. But this analysis seems to, suggest that you could make it.
If you the way I set things up, I never actually had to regulate the theory by putting in, by cutting off the supergravity theory at some scale epsilon. But if I start writing down things that have non-normalizable bits, I'd have to regulate it, and all those non-normalizable things probably can't be irrelevant. But yeah, I mean, normally there isn't. You go down dimensions where O2 and go to the fourth and so on irrelevant. Oh, you but what if I tried to do this trick and I wasn't in this range, so O squared is irrelevant? Okay, then if you do things carefully, you will find that if I put a cutoff, you'll find the integral obviously is stable. Right. Okay, so those are the two biggest subjects, and the only ones that really have a lot of equations with them. I mentioned orbitals and covered the main points. I just wanted to make a couple more points. So we're going in this direction of small perturbations of the theory, not the large ones, but not so large. Orbifolding is a fairly conventional way to bang on the theory. So if we have the 6 directions that are transverse to the free branes, and if we divide by we identify under some subgroup of the rotation group, then the origin becomes a singularity, but in a simple way, and the method of images, you get how this everything works. And so on the supergravity side, on the ADS side, you just take in S5 to S5 mod gamma, and on the CFD, you have some sort of quiver gauge theory. E.g., with ZK, you get, if gamma is ZK, you get, first of all, you get UF UN to the K in the gauge group, and then you get various bifundamental matter charged in different factors, and the details of the matter depend on, there's different ways for ZK, that ZK can act on the spatial coordinates and on the fermions, and so you get different kinds of bifundamental matter coupled into this group with n equals 2, n equals 1, and as Tom says, n equals 0 supersymmetry. Tom mentioned that in the n equals 0 case, as far as anyone knows, there are no conformal theories of weak coupling, right? That, you remember the weak coupling beta functions, right? I was reading your question, I thought you were talking about what the beta functions of the theory do, which are the perturbative beta functions. No, not in this. There are double trace operators. What happens in weak coupling is there are double trace operators that run. And I actually wanted to provide a strong coupling counterpoint to that. So in the case of, again, the amount of supersymmetry can be 2, 1, or 0. In the case of no supersymmetry, you're always worried about instabilities, and I want to tell you what they are. So in the first place, if some non-supersymmetric rotation, some supersymmetric rotation has a fixed point on the phi sphere, there's going to be some tachyon, and the theory will instantly be unstable. What happens generally with these localized tachyons is that some kind of hole forms in the space, and it gets bigger and bigger very fast. And your whole thing goes away. You have no grounding side. You don't have no gauge theory side. It's the general thickness that even when, in the non-supersymmetric case, even when you have no tachyons, even when there are no fixed points of the non-supersymmetric elements, you have the same process non-perturbatively. It's just Witten's decay to nothing, where this hole appears not due to a tachyon rolling down potential, but due to some tunneling process where the whole space tunnels from its original shape to this one, develops a hole, and then grows. So an example of the general phenomenon that non-supersymmetric theories are unstable. In this case, if you're willing to deal with metastability, and there's no reason that you shouldn't be, by putting some kind of UV cutoff on this space, you can, in the case that it's entirely instability, you can make the theory hang around for a long time, and encourage possibility. This is all I want to say about overall. counterpoles is that they don't, if you have, in the large n limit, this is inheritance. And so you basically take, and so in general, in the leading large n limit, anything that happens is the same to the overfold theory. If you have something that depends on the next order corrections, then not necessarily. Yeah. Also, once you overfold, you have new possibilities because there are operators in the twisted sectors which didn't exist before. But that gives you new possibilities. It doesn't destroy the original solution yet. So one can build new examples by combining RG flows and orbifolds. For the supersymmetric orbifold, you have new operators sitting at the fixed points, and some of them are relevant, and you can imagine turning them on, and now you have some singularity. It can be a whole ring of singularities, and the 5 sphere can turn into something like S3 cross S2. So you really can start getting into new topologies. And that's what the counterfold is, and by carrying this, again, it often takes some cleverness and some insight about the A-series side of duality to figure out where the flow goes to. There are people who figure this out. And this is a special case of a much more general thing, which is that the field theory is that on the gravity side, you can replace the S5 with any space, which is an Einstein space, in which the Ricci tensor is some constant, positive constant times the metric, and you still get a solution to Einstein equations with just 5-form flux. Actually, once you get into other fluxes like the 3-forms we were talking about before, you have more general shape. But if you stick to just the ingredients we have in the 88.5 theory, the 5-form flux and the metric, then you can replace with any Einstein space. And if you want supersymmetry, then there's